Hi everyone, today we're going to be talking about probability. Probability meaning, you know, the the percent chance the percent chance an event will occur. And, I say percent, but, oftentimes we talk about percentages as decimals. Um, so, for instance, say I want to find the probability of rolling an even number on a fair six-sided die. Well, how many even numbers are there, right? There's 2, 4, and 6, right? And there are 6 numbers total, so my probability is going to be, there are 3 ways I can win out of 6 possible, so 3/6 or 1/2. And if you like decimals, 0.5. So the general idea of probability is the probability that some event A occurs. Here in this example, A was rolling an even, is the number of ways A can happen divided by your total number of possible outcomes. Okay. So we can do maybe what's the probability of, and this is very basic probability of just counting. Say the probability of rolling a multiple of 3 on a fair six-sided die. Right. So my multiples of 3 that I have on a six-sided die are 3 and 6 are my only options. So my probability here is going to be, there are 2 ways I can win, 2 out of 6 possible, which is 1/3, and then in decimals that's 3, 3, 3, 3. You can go on and on and on with threes. Okay. And keep in mind with probabilities is they're very practical, meaning your probability can never be bigger than 1. Probability can never be bigger than 1, and it can't be any less than 0 either. So your probability will never be negative, right? There can't be a negative percent chance that something will happen. And no matter how confident you are, you can never be more than 100% sure of something, right? So in terms of probability, 1 is the highest it will be. And 1 meaning 1 here meaning 100% and 0%. So if you're ever working on a probability problem and you get an answer that is negative or bigger than 1, then something is wrong somewhere. Okay. We can make probability more interesting. Here there's several ways you can frame, counting your number of outcomes that you have. Something more interesting is maybe we have a coin. Okay. maybe we have a coin with heads or tails, and it's not a fair coin, meaning there's not an equal probability of heads or tails. So I have a coin, so flipping a coin. And let's say we're getting exactly 2 heads in 5 tosses, in 5 coin flips. And we're going to pretend this isn't a fair coin. The probability of heads and tails isn't the same, just to make it more interesting. So we're going to say a biased coin. You could say it's a biased coin or a weighted coin. And getting exactly 2 heads in 5 tosses, where we'll say the probability of getting a head is 0.6 instead of 0.5. So we're going to say the coin is a little biased towards rolling heads. So let's think about how we have to approach this problem. The probability of getting a head is 0.6, and we want to get exactly 2 of them. So if we want to get heads twice, that means we have to get, the probability of 1 time is 0.6, and then getting it again will be another 0.6. But we're doing 5 tosses, not 2 tosses, right? So there's still 3 tosses of probabilities we need to consider. So if the probability of getting heads is 0.6, that means the probability of getting tails is 0.4, right? Because they're opposites. These are called complements of each other. So if you have the probability of some event, right, and you wanted to look at the complement meaning the complete opposite of the event occurring, we'll use a bar to denote that. That's 1 minus the probability of A. So here A and A bar they're called complements. Complements meaning they are complementary to each other. Complementary to each other meaning that if you consider them together, you get all the possible outcomes. Just like here, if we consider heads and tails together, that is all the possible outcomes when you flip a coin. You can get heads or tails, and that's everything. So these are complementary to each other. So their probabilities are going to add up to 1. So back to this problem is we have these 3 more coin tosses we have to do because we're doing 5 coin tosses. So the probability of getting tails is 0.4. And we're getting a tail 3 times because we're only getting heads once. So we have this big probability here. Well, not big in value, but a long multiplication problem. And there's still one more thing we have to consider, because if we flip a coin, and we're using this as the probability, let's see what this flip represents. This represents heads, heads, tails, 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 right? But that's not the only way we can do this. We can get, for example, heads, tails, heads, tails, tails, right? That's another option. So we have to consider all of our possible options we have. I'll move this down. So what are all the possible options we have? Heads, tails, tails, heads, tails, heads, tails, 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 heads. So those are all the ways we can do it with heads coming first. So tails, heads, heads, tails, 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 heads, tails, heads, tails, tails, head, tail, tail, head. Running out of room again. I have to move this. So those are all the ways where your first heads come second. So next is tails, tails, heads, heads, tails. Tails, tails, heads, tails, heads. And then tails, 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 heads, heads. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 possible ways we can do this. There's 10 possible ways we can get 2 heads in exactly 5 tosses, right? So there's 10 ways I can order these numbers, right? If I was doing this one, then it would be 0.6, 0.4, 0.6, 0.4, 0.4, right? So really we get this probability here a total of 10 times. So the probability is that times 10, right? So in general, we look at, we'll say the probability that I'll say x equals 2 for getting exactly 2 tosses, x representing the number of heads. Or in general, say for any number, we'll say k. Right, k I'm using to represent a number. We have to look at, remember, it's the probability that x happens, right? So, but x is happening this number of times, so we have to do it that number of times. For instance, here we're doing 0.6 squared, right, because 2 heads and the probability is 0.6. And then we're doing 0.4 3 times, right, because we're doing it 5 total. We've used 2 of them already, so 5 minus 2 is 3, right? So this is going to be 1 minus p and then n minus k, where n is your total, your number of trials, we'll call it. So here in our problem, n was 5 because 5 flips, 5 trials of this experiment here. And then we have to multiply that by the number of ways this can happen, right? So the number of ways that can happen we represent as n k, right? It's in these parentheses, it's not a fraction, there's not a bar in between here, this is just notation. And how this reads is n choose k, right? This is the number of ways I can get this many heads in this many tosses. This is the total number of ways I can choose k number of things from a group of n things. And there is a formula to calculate that. N choose k is equal to n factorial over k factorial times n minus k factorial. And if you don't remember what factorial means, this exclamation mark, for example, if I wanted to calculate 5 factorial, that would be 5 times 4 times 3 times 2 times 1, which is, let's see, 20, 60, that's 120. Right. So it's multiplying the number starting with itself all the way down to 1 is how factorial works. So like if we wanted to work out the problem we just did with 5 choose 2, how many ways we can get 2 heads and 5 tosses, plugging that into this formula, we get 5 factorial over 2 factorial times, so n minus k. So 5 minus 2 is 3 factorial. So if we wrote this all out, this is 5 times 4 times 3 times 2. I'm going to leave off the 1 because multiplying by 1 doesn't do anything. 2 factorial is 2 times 1. I'll leave off the 1. 3 factorial is 3 times 2. And a lot of things cancel, right? This 2 cancels, this 3 cancels. 4 divided by 2 is 2, and we're left with 5 times 2, which is 10. Right? So the formula agrees with this listing out we did on all of these. So this gets a lot harder to do, when there's a lot more possibilities, but when the 5 and the 2 are much larger. So you can do it by hand, but sometimes it could be much harder and longer, or we can use software to help us, which is where we're going to switch to RStudio. And here we can do all of these calculations and different variants of this in R. So if I wanted to calculate 5 choose 2, how many ways I can get 2 heads and 5 tosses, I can use the command choose. Okay. So how many ways can I choose 2 from a group of 5? And we know now that this should give us 10. Yep. And then changing the numbers, if you wanted to toy around, 15 choose 5, 3003. So we didn't change the numbers too much, right? I mean, 15 and 5 are still relatively small numbers, but you see the number of combinations becomes very, very large very quickly, depending on how these numbers are chosen. So this type of problem that we're solving right now is a binomial distribution problem. Binomial distribution. Binomial, so bi meaning 2, right? So doing probabilities when there are only 2 possible outcomes and you're doing a set number of trials. So this is the general formula for calculating binomial probability. And the command in R to do this is dbinom. Binom for binomial. Again, bi meaning 2. And then D for distribution. So we want to do 2 heads in 5 tosses where the probability of getting head is 0.6. The order you put these in does matter. If you change the order, it'll give you an error or give you the wrong value. So dbinom, doing the probability of flipping 2 heads in 5 tosses where the probability of tossing a head is 0.6. Sorry you can't see it all because I have split screen between these right now. So we calculate this probability and we get 0.2304. So let's go ahead and calculate this by hand. We did, not by hand, but we'll type it out. We did 10 times 0.6 times 0.6 times 0.4 times 0.4 times 0.4. And see, we get 0.2304, right? So we did it correctly, which is nice. And then a bunch of variants of this same type of problem. Say you wanted to compute the probability of flipping no more than 2 heads. Whoops. Of flipping no more than 2 heads. So no more than 2 means it could be 0 head, 1 head, or 2 heads, right? No more than 2 means I can flip 1 head, I can flip 0 head, 1 head, or 2 heads. So what you could do is just do 3 of these, 1 for 0 head, 1 head, and 2 head, like we have right here. And we get 0.31744. So the tricky part about these problems is figuring out the wording and just knowing exactly what they want. For instance, exactly 2 versus no more than 2. You could have it say at least 2, less than 2, all kinds of different wordings, and you just need to be aware of what they're asking. There's another way you could do this. Maybe we're dealing with larger numbers and you don't want to type out multiple of these over and over, you can use the command pbinom. So notice the difference, p instead of d. In pbinom, we look at a range. So by default, it's going to look at everything less than or equal to the number you tell it. So if we're looking at no more than 2, meaning 2 or less, 2 or fewer, we put in a 2. If it wanted to know less than 2, then we'd have to put in a 1, because if you put 2 in here, it's going to automatically include it. And this will give you the same answer. So this saves you a little bit of time in case there are, more than 3 or more than a manageable number of these to type out manually. And say you wanted the complete opposite, more than 2. Well, if you want the complete opposite of something, we saw we can do 1 minus because they are complementary. And another thing you can do is, again, by default, this looks at everything less than or equal to 2. If you wanted it to look at everything greater than that instead, we can use this command lower tail equals f. F stands for false here. So F stands for false. You don't have to type false out all the way, but you can. So this is saying, okay, instead of looking at everything on the lower end, meaning anything at this value or below, we're saying that's false. Now, so if it's false that we're going to look at anything 2 or below, that means we're going to look at anything bigger than 2. And we get the same value here. Okay, so the different homework problems you'll see are just different play on words, whether it's exactly or more than or no more than or whatever kind of combination you can think of these words. So that's the tricky part here. Other than that, it's just plugging in the numbers properly. So that is binomial probability. Another type of probability we're going to look at is probability using the normal distribution. And the normal distribution is nice. It's very common. Some key points about this is that it's symmetric. And it's bell-shaped. It's an example of something called a density curve. A density curve means that the total area under the curve is 1. So I'm going to sketch what this looks like. I'm doing it by hand, so it's not going to be as good as an image you may see in your textbook or if you look up normal distribution. And a normal distribution is determined by a mean and standard deviation. So sometimes to denote a normal distribution, you'll see n for normal, mean, comma, your standard deviation. Okay. And we label the axes traditionally going up and down by your standard deviations. Another interesting thing is that when you're within 1 standard deviation, that contains 68% of your data. And when you're within 2 standard deviations, you can that area contains 95% of your data, which is interesting. It's not exact, but it's close, off by some small decimal, some small fraction, but close right there. And if you went three standard deviations out, then it would be 99.7% of the data would be contained within 3 standard deviations. That's called the 68, 95, 99.7 rule. I don't know that it'll come up much in your homework problems, but it's an interesting thing that we see. And again, this is a density curve, meaning the total area is 1 under the curve, right? Meaning 100% if we went forever in both directions. This extends forever in both directions, right? It just gets closer and closer and closer to the 0 line, but it never hits it. So again, the normal distribution is determined by a mean and standard deviation. Whenever you're doing any of these problems, you need a mean and a standard deviation. So computing probabilities with this is very, very, very difficult to do by hand. Nobody does it by hand. Back a number of years ago, the popular thing was people had printouts of a bunch of different tables with different numbers, and you had to follow a large table to figure out your probabilities, and they weren't always exact. They're always off by a certain amount because there's an infinite number of ways we could of possibilities here, right? There's an infinite number of spots along this line you could be interested in. We can't have infinite number of probabilities in a table to look at. So nowadays it's much nicer with software to be able to do these problems. So let's look at an example here. And these numbers in this example are not accurate. I just made these numbers up. We're going to assume the height of Fontbonne students is normally distributed with a mean of 68 and a standard deviation of 2.5. So I'm going to draw my normal distribution. Okay, and the mean I'm saying is 68, so 68 is right in the middle. And the standard deviation I'm saying is 2.5, so I'm going to count up by 2.5. So this is going to be 70.5 and then 73. This is going to be 65.5 and 63. Okay. And I want to say calculate the proportion of those with heights less than 65 inches. Okay. Less than 65 inches. So less than 65 inches is right about here. Right? It's not exact, but right about there. So what this is asking for is what is the area under the curve in this region is what this is asking. What the area under this curve is. And like I said several years ago, the popular and common thing to do was to look at tables. And then the issue was all the tables were different. Every textbook had the tables organized differently, and it wasn't consistent, it wasn't efficient, it wasn't that precise. But software helps us a lot. So we're looking at a range of values. So anything less than 65, right? And this is a continuous distribution, meaning we could look at any decimal you could possibly think of on here. Whereas in the coin flipping example, we only had a limited number of options, right? When flipping a coin 5 times, we could get ahead 0, 1, 2, 3, 4, or 5 times, right? But we couldn't get ahead 1.5 times, right? Because we can't. That's not possible in that context. So this binomial was a discrete probability distribution. Let's write that down. This was a discrete probability distribution. And normal distribution is a continuous probability distribution. Okay. Continuous meaning we could land, like I said, anywhere we possibly could want on here. We could land. We're not limited by anything. It doesn't matter how fine the decimal is or anything. You could land anywhere. And because of that, if you were ever interested in a single number, right? Like here we're looking at a range of values here, not a single value. The probability is always going to be 0, right? Because there's an infinite number of options we have, and if we looked at this formula we talked about earlier here, it would be 1 over infinity, which is 0, right? So if you ever wanted to look at one number and only one number, the probability we randomly pick someone and their height is exactly this decimal, it's basically 0. So in R, we can use the p-norm function. Remember, just like how we had p by nom, it by default looks at everything less than or equal to the number you tell it. So we're looking at everything less than or equal to 65. And I say less than or equal to, but this is asking for strictly less than, not less than or equal to. And that doesn't matter here, because the difference between less than 65 and less than or equal to 65 is one includes 65 and one doesn't. But we talked about already that if you're interested in one number and one number only, like just 65, that probability is going to be 0, because it's going to be, there's a 1 out of infinity chance of getting exactly 65. So the difference is 0 between those two. So it's okay here. So being p-norm, again, by default looks at everything less than or equal to what you tell it. Probability of less than or equal to 65, or the mean is 68 and the standard deviation is 2.5. The order you enter these numbers does matter. If you change the order, you could get an error or get a wrong answer. I'm going to go ahead and clear this with the broom here. So that is saying that the probability is 0.1150697. So that says that in this shaded area, that is 11 point, we'll say, I'll round it, 51% of the data. The probability you randomly pick someone is 11.5%, roughly. And again, what if we wanted, instead of less than 65, we wanted greater than? We could do the same thing we did above in p by nom, where if you wanted the opposite end, you could do lower tail equals false. Or again, you could do 1 minus. So compute the proportion with height greater than 65 when we still have the same mean and standard deviation here. You could have this lower tail equals false, or you could do 1 minus, and I just copy pasted. Either one of those works. And as a visual, that's giving you this area. Let me clean this up. That's giving you this area here. And it's saying that that is 0.8849. 0.8849 is 88.49%. And notice that when you add these two up, you get 100%, right? So it's all, we can check ourselves and make sure that the answers make sense with each other, and they do here. Okay. All right, I'm going to make a copy of this so I don't have to redraw it. And I'll clean it up a bit. Get all these little details. Oops. Oh well, good enough. Now we're looking at the probability or proportion of those, sorry, this keeps moving, with heights between 65.5 and 70.5. So we're looking at this range, 65.5 and 70.5. Right. So what's the probability? We randomly select someone and they are within this range. That's the same thing as saying the proportion of those with heights in between this range. So this is interesting because this is exactly one standard deviation below the mean and one standard deviation above the mean. And we talked about this earlier, is that we expect that to be about 68%. So that should be 68%, right? So what we're finding in this problem is the area under the curve between these two values. And that should be close to 68% because these are exactly one standard deviation above and below the mean. So the way we can calculate that in R is, again, P norm looks at anything less than or equal to the number you give it. So if we wanted just this shaded region, what we'd have to do is look at everything less than or equal to 70.5 and then subtract everything less than or equal to 65.5, right? So we have to do this outer red area minus this pink area to be able to get this orange area here. You see that visual? So that's what we're doing here. We're doing the probability that we are less than 70.5 minus the probability that we're less than 65.5. Because what that's going to do is we have that red area. Again, we have this red area here. We have this red area here. And we are taking away the pink. We're taking away the pink. So we're getting rid of all of this space. And we're going to be left with just this space here, which is what we want. Okay. So we're looking at everything less than 70.5 and subtracting everything less than 65.5. And we get, look at that, 68 point. This turned out to be, whoops. This turned out to be, like we said, it's going to be around 68. 68 point, we'll say 27%. And now what if you wanted to ask a slightly different question, right? Here we're told the numbers and we want to see what percentage or what proportion falls in that range. But now we can change it to say, okay, how tall do you need to be in the 90th percentile? Meaning, how tall do you need to be taller than 90% of students? Okay. Or another way we can say that, how tall do you need to be in the top 10 of students? Well, you can use the Q norm command. So Q for quantile, norm because we're using a normal distribution. So what value do you have to be in the 90th percentile where your mean is 68 and your standard deviation is 2.5. So again, to make a visual of this, I'll copy this. I'll clean this up. So now what I'm saying is what number do I need to be on this axis here? Where do I need to be on here so that when I look at this probability or this proportion, I want this entire proportion to be 90%. So I'm asking, okay, what number does this have to be for that to be the case? And that's what this answers here. So this is saying that if I run this, 71.2 is the magic number you need to be at. If you're that many inches tall, then you are taller than 90% of Fontbonne students. And again, that's not necessarily true. I made these numbers up for the mean and standard deviation. And you could think about it the other way. You can think 90th percentile, or you can think top 10%. And when you're thinking top 10%, 10% is 0.1, and top, instead of looking at the bottom, you could look at the top again with the same lower tail is false argument you can put in there, and you get the same value. So one way we talked about significantly high and low values before is that you can be 2 standard deviations above and below the mean. And the reason behind that is that we see if you go 2 standard deviations above and below the mean, when we talked about that, gives you 95% of the data. So it means you're in the extreme 5% either way. It means you're in the top 2.5% or bottom 2.5%. We can easily change that top 2.5% and bottom 2.5% to be top and bottom 5%. And that's commonly... That's another common rule of thumb. You can talk about 2 standard deviations above and below the mean. Another way of talking about significantly high and low values is looking at the top and bottom 5%. So maybe like here being 5%, and what does this value have to be, or here and this being 5%, and finding out what does this value have to be. This was a very bad percent symbol. There we go. So this could be used in several different kinds of applications. One application we're looking at here is assume heart rates are normally distributed with a mean 74 beats per minute and standard deviation 12.5 beats per minute. What heart rates would be considered significantly high or low, right? If you're going for a checkup or you have some medical concerns and they check your heart rate, your heart rate, if it's too high or too low, that may be an indicator that there's some medical concern that needs to be addressed. So we can calculate this based on these parameters. What heart rate do you need to have to be in the top 5% or bottom 5% to be considered significantly high or low? So we can use the same Q norm, right? We can say the bottom 5% being significantly low and the top 5% to be significantly high, right? The only difference here is lower tail is true versus false. And for true, it's true by default, so you don't necessarily have to have this piece in there. I just had it in there for just to show that the only difference is this true versus false statement here. So this is saying that if your heart rate is 53.4 or below, you're significantly low, and 94.5 or higher is significantly high. And I assume these are resting heart rates, not heart rates after you're done working out or going for a run or something like that. Okay. And then the last thing to touch on is this thing called z-scores. And we had this idea before with coefficient of variation. Remember, coefficient of variation was your mean divided by your standard deviation. Remember that? It was your mean divided by your standard deviation. And the idea was you're able to compare groups that aren't measured on the same scale, right? We talked about, I think it was heights and house prices. Heights are in the tens of inches, or usually no more than a few feet or several feet. But housing prices are in the hundreds of thousands of dollars. So to compare those types of distributions, you need a way to scale it down. And coefficient of variation was the way we did that. With normal distributions, we talk about z-scores. And the way that's calculated is, or what it really is the number of standard deviations from the mean. So instead of saying you're 10,000 over the mean or 5 over the mean, on drastically different scales, we talk about, okay, relative to your own distribution, how many standard deviations are you above the mean? And that's calculated just as you would think, where you take your value minus the mean, right? That is your distance from the mean is all that is, right? Divided by your standard deviation. And I'm gonna switch back to this notation here with mu's. Okay. So it's your distance from the mean, right? How far you are above or below the mean, right? If x is higher, this is going to be a positive number. If x is lower, it's going to be negative, divided by your standard deviation. And we can calculate those quite easily. So I'm going to save these two numbers. I'm going to save this one as x and this one as y. I'm going to go ahead and clear the console too. So to be in the top or bottom 5%, let's see how many standard deviations that is. The mean was 74 beats per minute. So I'm doing my value, which is this, minus the mean divided by the standard deviation. So to be in the top or bottom 5%, to be significantly high or low in any normal distribution, you have to be 1.64 below or 1.64 above your above the mean. That many standard deviations above or below the mean to be in significantly high or low regions. So this covers chapters, I believe it's 4 through 6 in our textbook. Again, I do encourage you to read that as supplemental material, and with this you are able to do the next homework assignment. Please email me if you have any questions on any of this material or anything in the homework. Take care.